Hello everyone, today we're solving LeetCode 79 word search. Alright, hello everyone, today we're solving LeetCode 79 word search. Given an n by n grid of characters board and a string word, returns true if the word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally and vertically neighboring. The same cell may not be used more than once. Alright, so let's look at the first example here. This grid should return true because we can visit all of these letters in our test word by traveling the grid horizontally or vertically. As you can see, we can go from A and we go to the right to find B, to the right again to find C, down for the second C, down again for the E, and left. And we've spelled the entire word, so this should return true. Right? All right. And for example, if we're at the letter F, we can travel to B, C, D, and S, but we cannot travel to A because that would be a diagonal traversal, and that is strictly against the rules. All right, so now that you understand the problem in a high level, let's get into how we'd solve it. First, I always like to set up my problems with all the tools we need. First, we need a way to go up, down, left, and right in the grid because those are the directions we're allowed to travel. Next, we need a scene, and this will just be a set that's going to contain cells that we visited already because the problem states that we cannot visit a cell more than once. And next we have IDX or index, and this will just denote what letter inside of our target word we are currently searching for. All right, for example, when we first go into our algorithm, we'll be looking for the letter S with index 0. All right. So I'm going to quickly walk you guys through how we'd solve a problem like this. So index start off at 0. And scene is of course empty because we haven't visited anywhere. Now let's think about what is the entry point for a function like this. Well, we can't spell the word C starting at the letter B, right? So we need to find where in this grid do we have the letter S or index 0 in our word, because that is be the entry point. Because the only way to spell C is to find an S. So what we do is traverse this entire grid. And for example, we go A, B, C, E, and then ding, 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 we're at S right here. Now, what we're going to do is look up, down, left, and right and see, hey, we found index 0. Now we're searching for index 1. We're going to look up, down, left, and right and see, can we find index 1? And since we've already visited this S here, we're going to add that to scene. So we'd add 0, 1 for the cell that we're currently at. And now we look around. So we look up and we see that's an A. We're looking for index 1, which would be an E, so we can't traverse there. Look to the right, that's an F. Same story. We look down, that's an A. And we look to the left, and that's out of bounds. So that means from this entry point S, we cannot travel to any adjacent square to help us get to the word C. So that means that we need to continue searching. Right? So we start off at S, and we found out that there's no way to spell C from there, so we continue going. So we go from S to F to C. And we see another S right here. And same story here. We found index 0. So now we're searching for index 1. The scene has to add the cell that we've already been to so we don't travel to it again. So this would be 1, 3. And now we look up, down, left, and right. We look up and we say, hey, we're looking for letter E. This is letter E, so let's traverse there. All right, so now we're at E. And we have to make sure to add that into our scene so we don't travel back to it. So we add 0, 3. And from here, we do the same thing. We say, hey, look to the up. That's out of bounds. We can't travel there. We look down. We just came from that cell, so we can't go there. We look left. Left is a C, and we're looking for an E because we're looking for index 2 here, right? And we look to the right, and that's also out of bounds. So that means we only could spell SE, not SEE, and there's no other place to go. So that means that we need to backtrack back to the S, since we know that traveling up will not get us the answer. So we need to find another way, because we need to exhaust all of our options. So we're still looking for index 1 because we see a S right here is index 0. Let's try another way. Let's look down. We look down and we say, hey, all right, that's an E, and we're looking for the letter E, index 1. So we're going to traverse there. And remember, we got to add that to scene because we're currently at that cell. So we're going to add 1, 3. All right, remember, we have to add the cell that we're traversing to. So that'd be 2, 3. So now we're at the E. And since we found this first index, we need to now look for the second index. So IDX is now at 2. So we're searching for the second index in the word C. All right, we do the same thing. We look up. We just came from there, so we can't search there. We look down. That's out of bounds. We look to the left, and we say, hey, we're looking for the letter E, and this is the letter E, so let's traverse there. Same story here. We add that to our scene, so that would be 2, 2. Traverse. So now we're at the E, and we're going to call DFS again, and we're going to move IDX up one more time. So it's going to be 3, right? Let me fix that up. So now we're looking for the index 3. As you can see, Word doesn't actually have an index 3, which is the interesting part. Since we're using DFS, we're going to use a base case. We're going to say, well, if the index is equal to the length of the word, that means we've completed the word, because that means we've passed all indices and we found a letter that matches to each one, right? So 3 is the index. The length of this word is 3. So if 3 equals 3, that means return true because we've spelt the word, right? So this just returns true. So hopefully that makes sense on what we do here. Just to quickly recap, we're going to have our directions up, down, left, and right. We're going to have a scene to ensure that we do not go to the same cell twice. And we have index, which is just going to denote what letter we're looking for in the word. And if the index ever gets equal to the length of the word we're searching for, then we know we've completed the word, so we return true, right? Otherwise, false. So let's go into how we'd code up a solution like this. First, let's make our up, down, left, and right, or otherwise our directions. I just like to call it direct. And we'll have that equal to an array of tuples. And this is the interesting part. If you've never done like a matrix traversal, this would be very good practice. So let's say this cell here is 0, 0, A. How do we go to the right? We need to add 1 to the column. So we go from 0, 0, which is the A, and we want to go to the B. That'd be 0, 1. So that means we add 1 to the column, right? Because this is the row, this is the column. So we add 0 to the row, 1 to the column, and that's like us going to the right. Now let's go left. We'd keep the row the same, and we'll do -1 to the column to move backwards. So in other words, left. Let's go up, and next we're going to go down. So you could pause and think about what that would be, but we'd add 1 to the row to go down, but keep the column the same. And for up, we'd go -1 to the row and keep the column the same. Just to quickly show what I mean here. Let's say we're at 0, 0 yet again, but instead of going right, we want to go down. So that means we'd have to add 1 to the row and keep the column the same. So as you can see, the row increased, and now 0, 1, 0 would be the S. So that's like going down from A. All right. So we have our directions. Now what we have to do is create our depth first search function. So DFS, we'll define function DFS. And what do we need? We need first the row. We need the column. We need our scene set to tell us how many cells we visited. And we need our index, right? And before we do that, I always like to just make a couple variables. I like to call this rows equals length of board, and calls equals the length of board at index 0. Just so we can have the length and the width of this board in 2 variables, right? First, so since we have a DFS function, first we always want to take care of what is the base case. The base case is if IDX equals the length of word. So if the IDX gets to the end of the word, then that means then we need to return true because we've spelt the entire word. Next, what we have to do is if we're given a row and a column, that means we're plopped onto this board. We need to look up, down, left, and right. So what we do there is say for R, C in direct. So that's going to take in the row and the column. And we need to say, well, new row, or in R for new row, equals the row plus R. And the new column will be the same thing. So new column equals call plus C. And just to reiterate, let's say we're at 0, 0 and we want to go down. We add 1 to the row and 0 to the column. So 1 plus 0 is 1, 0 plus 0 is 0. So and 1, 0 is 1 down from 0, 0. All right. So that's just us traversing the grid and horizontally and vertically. Next, what we want to do is to make sure we don't go out of bounds. Let's say we're at A. We don't want to go up or to the left because that would generate a list out of bounds error and our program wouldn't even run or wouldn't finish running. So what do we do for that? We say if 0 less than or equal to new row and less than rows. I'll quickly explain what this means. We just want the new row to be greater than or equal to 0. So it's not anything less than 0 would be back here, which is out of bounds. And we don't want it to be greater than rows. As you can see, rows goes up to 3. We don't want it to go any farther than this cutoff point. So let's just make sure is that any row that we're going to look at seriously is going to be in bounds. It's just an inbounds check, right? If we do the same thing for columns to make sure it's inbounds, column, and it has to be less than calls. And that's why I made these variables up here. So I don't have to write length of board and length of board 0, right? And if this doesn't make sense, it didn't make sense to me the first time. Make sure you just actually pause and then look at this line of code and see how it keeps our cells inbound, right? So this checks if it's inbound. So next we have to check if the cell that we're currently looking at has been traversed to before. So we say, hey, well, and new row, new column, not in scene. So if it's not in scene, so if it's in bounds and not in scene, so it's a fresh cell and it's in bounds, what's the last thing we need to check? We need to make sure it's the right letter. So we have to say and, one more and, I know it's a really long if statement, board at new row, new column equals word at index. Just to recap what all of this does, we're checking, hey, is the cell we're looking at in bounds? Is the cell we're looking at been traversed to before? And if it has not been traversed to, this we continue. And is the cell that we're looking at equal to the letter that we're searching for, right? So this is all we need to know. So if all these things are true, then that means we need to add that cell to scene because we're going to traverse to it. So we're going to say scene.add, and we need to do new row, new column, right? All right, so next, make sure you pay attention here. Since our DFS will return either true if the word is found or false if not, we actually can use that to our advantage. We could say if DFS, and we plug in our variables. So we say new row, new column, scene, and we're going to index +1 because we want to look for the next letter. And if that evaluates to true, and the only way it can get to true is if we get to the last word in our word and we found everything. So that means that we found the word. We need to return true, right? If that doesn't happen, that means our DFS was not able to find the word. So what do we need to do? We need to remove that cell from scene. Just like when we were traversing the first time here, when we're at S, we don't want that scene to transfer over to when we're over here, right? Because once we found out a path doesn't work, we need to reset the scene. So we say scene.remove new row, new column. All right. Beautiful. And if all of that runs and we're not able to find the word, then we need to return false. So we say return false. Perfect. So that takes care of our DFS function. Now we need to know, how can we actually get into this DFS function? Remember, when do we actually call it? Well, we call it whenever we find a letter that is equal to the first letter in the word. So in this case, A, we have to traverse the entire grid until we find an A, and we call DFS on that right here, and we'll run this logic. All right, so to traverse a grid, we say for row in range rows. And remember, rows is just the length of the board. And for call in range calls, and this is all the columns inside of our board. All right, so we're traversing the grid, and we need to say, well, if we find a cell that is equal to our entry point to our DFS, i.e. the cell is equal to the first letter in the word. So let's say we're traversing this board here. Once we find an A, we want to enter DFS so we can search and see if we could find the rest of the letters from a horizontal or vertical traversal. So we say if board at row call equals word at index 0, we need to call DFS. So we know that DFS will return either true or false. So we say if DFS at row call, and for scene, we're going to make a set and add the row and the column because we don't want to traverse here again because we've counted as our first letter. And lastly, we're going to be looking at, instead of index 0, we're going to start off at index 1 because this would be considered index 0, right? And if that evaluates to true, then we want to return true. All right, and if it gets all the way down here without returning true, then we just need to return false. And let's try that out and see how we did. Hopefully we haven't made any mistakes. There we go. We solved the problem and it's relatively efficient. If you guys are curious about any optimizations, maybe I can make an updated video to this, but I wanted to show a beginner solution. So hopefully you enjoyed the video. Peace. Make sure you drop a like.